Hello students, welcome to class 12 physics. In this video we are going to discuss about the Lenz law of chapter 6 electromagnetic induction. But before discussing the Lenz law, let us see a short question. On passing current through a solenoid, which of its end behave as north pole or south pole? Explain. When current flows through loop or coil, it behaves as a magnet. Its one phase behave as north pole while opposite phase will behave as south pole. Which end of coil behave as north pole and which end behave as south pole can be found by following method. First, when closed current loop is viewed normally and if the current seems to flow in clockwise direction, then that side of the loop behaves as south pole and the other side of the loop behaves as a north pole. Here, as you can see, we already know that when current is passing through the solenoid, then the magnetic field is generated. That means it is magnetized. So the coil will be behaving as the magnet. If something is behaving as magnet, right? If the solenoid is behaving as magnet, then it will be having the north pole and south pole. So take the coil, right? And if you are standing normally in front of the coil, right, as you can see over here, and if the current is passing in the clockwise direction, if the current is passing in the clockwise direction, then the end that is facing towards you behaves as the south pole and the opposite end behaves as the north pole. In the same way, when you are standing normally in front of the coil and if the current is passing in the anti-clockwise direction, then the end towards you behaves as the north pole and the opposite end behaves as the south pole. That is the second point. Similarly, if the current seems to flow in anti-clockwise direction, then the side of the loop towards the eye behaves as north pole and the other side as south pole. So this is the method how you can know the poles of the solenoid in which the current is passing. So you may note down this theory. Now let us discuss the Lenz law. Prove that the Lenz law is a specific representation of the law of conservation of energy and state Lenz's law. In 1834, German physicist Heinrich Friedrich Lenz deduced a rule known as Lenz's law, which gives the polarity of the induced EMF in a clear and concise fashion. The statement of the law is as follows. The polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produced it. The negative side shown in the equation epsilon equals to minus d phi b by dt represents this effect. That means this negative side shows here what? That the time rate of change of the magnetic flux that produces the EMF, and because of this EMF the current is induced. This current induced will oppose this change in the flux. As you can see in the figure, there is a bar magnet, a coil connected with the galvanometer, and the north pole of the bar magnet is facing towards the coil. So when you take this bar magnet near to the coil, then the magnetic flux linked with the surface will increase. So there will be increase in the magnetic flux with the coil when the magnet is taken near to the coil. So due to that the EMF will be induced, and due to the induced EMF, the current is also induced. So what this current will do, it will oppose this change in the magnetic flux. That means this current will decrease the magnetic flux. That means what? It will decrease the magnetic flux. That means it will be taking this bar magnet away from it. So when can this occur? When this end of the coil behaves as the north pole. Then and only then there will be a force of repulsion and the bar magnet will be moving away from it. So in such case, this end becomes the north pole and the opposite end becomes the south pole. So according to the short question that we have seen right now, that when the current is passing through the coil, the solenoid behaves as the magnet. And if the current, when you are observing, suppose you are observing from this end, then when the current is passing in the anti-clockwise direction, then and only then this end behaves as north pole and the opposite side behaves as the south pole. So what happens when there is increase in the magnetic flux? The induced EMF and thus the induced current will oppose this magnetic flux. That means it will try to decrease the magnetic flux, taking the bar magnet away from it. This can occur only when there is force of repulsion. That means this end behaves as north pole, this end behaves as south pole. That means the current direction is anti-clockwise. So this is how we can know the direction of the current. In the same way, when you are taking the bar magnet away from the coil, that means when there is decrease in the magnetic flux, then also the EMF is induced in the coil, thus the current is induced. But now the current that is induced will increase the magnetic flux. That means what? That means it will be taking the magnet near to it. So when can this occur? When this end of the coil behaves as south pole and the other end behaves as the north pole. So in such case, this will become the south pole of the magnet, this will become the north pole of the magnet. So this happens only and only when the current flows in the clockwise direction. So this is how we can know the direction of the current with the help of the Lenz's law. In figure, we see that the north pole of a bar magnet is being pushed towards the closed coil. As the north pole of the bar magnet moves towards the coil, the magnetic flux through the coil increases. Hence, the current is induced in the coil in such a direction that it opposes the increase in flux. This is possible only if the current in the coil is in counterclockwise direction with respect to an observer situated on the side of the magnet. Note that the magnetic moment associated with this current has north polarity towards the north pole of the approaching magnet. Similarly, if north pole of the magnet is being withdrawn from the coil, the magnetic flux through the coil will decrease. To counter this decrease in magnetic flux, the induced current in the coil flows in clockwise direction and its south pole faces the receding north pole of the bar magnet. This would result in an attractive force which opposes the motion of the magnet and the corresponding decrease in the flux. Next, we have seen that this Lenz law is specific representation of law of conservation of energy. That means what? Here it will be obeying the conservation of energy. That is, energy can neither be created nor be destroyed, but it is transferred from one body to another. So here also what is happening? Because the magnet is in motion, it will be acquiring the kinetic energy. It will be moving with certain energy. So when it is moving, it will be imparting some of its energy to the charges due to which it is in motion. It comes in motion and due to which the current is produced. So, as for example, if a person is running in the race, then it will be running with some of its kinetic energy. It will be moving with certain velocity and thus it will be having its kinetic energy. But while running in the race, if some object gets stuck into its leg, then its speed decreases. That means its kinetic energy decreases, and the object that is stuck to its leg, that will come in motion. It is not moving, the object is not moving with its own energy. So the energy with which it is moving is imparted by the person. So the kinetic energy of the person decreases, and that decrease of the kinetic energy is being given to the object. So as a whole, as a system, the kinetic energy, the energy remains same. So here the energy is transferred from one body to another. So in the same way, the kinetic energy of this magnet, that energy is imparted to the charges in the coil, and taking that energy, it moves in the coil and the current is induced. So in this case also, energy is transferred from one body to another body. But as a system whole, the energy remains same, it remains constant. So we can say that this law is the representation of the law of the conservation of energy. So students, you may note down this theory.